Postgres. So in this talk, Chris, who came from Indonesia to here, thank you, Chris, and he's going to talk about the crazy things that you can do with Postgres indexes. Thank you.
Thank you very much, and also thank you very much, Defram, for the introduction and all of your help on the volunteer side. So this talk is crazy things you can do with Postgres indexes, and I'm going to get to the scope of this talk because in some ways this is more limited than you might think, but by making it more limited we can also dive deeper into some of the crazy applications you can do with indexes. Now, I have 24 years of Postgres experience. I've been using Postgres since 6.5, back before we had write-ahead log, and if you tripped over a power cable, you might be restoring from backup. So I've worked with Postgres in many roles as a developer, database administrator, built Postgres teams, done a lot of stuff, even contributed a few patches, one of which has been accepted. So. This talk, we're going to talk about theory, we're going to talk about practice. Oftentimes we think about indexes primarily as performance tools. And I'm going to show how we can take them to solve some performance problems that go a little bit beyond indexing, but I'm also going to show about how you can sometimes add functionality to your database by using an index, which is a little bit counterintuitive to the way we typically think about indexes. Now, I'm only going to be talking about Btree indexes in this case, right? This is the narrowing part. So I'm not going to be talking about gin or gist or the further types like rum or the ability to write your own indexes. That, of course, opens up even more doors to things that you can do with Postgres indexes. But in this case, just talking about Btrees, Postgres has some really interesting aspects of indexes that oftentimes are underutilized, but may require a bit more understanding to use. And we're also going to talk about the cost of each of these approaches because, very oftentimes you go out, you find out all kinds of new tools, you end up with hammer syndrome, oh, this is a nail, this is a nail, this is a nail. If you aren't thinking about the complexity costs, you may create more problems for yourself. So I want to start by defining a function in this context. And I'm also going to define a relation. We all are relational database users. We think we know what relations are, what functions are. Sometimes it's really helpful to make sure we have clear, concise definitions for these things, so I'm falling back on the mathematical definitions. A relation is a set of corresponding facts, okay? In relational databases, anything first normal form and above, we're dealing with, actually second normal form and above, we're dealing with relations in our tables, okay? So we have one fact corresponds with another fact. This is what a relation is, right? Almost all the time, if we're working with third normal form and up, actually even second normal form and up, no, third normal form and up, we are dealing with functions also. A function is a relation such that the domain is unique, right? So you have a fact set that's a domain, and then you have correspondences to that, right? You can know a function because for a given input, you will have a given output, but also, this need not be input and output. They can just simply be seen as correspondences. And so, like, when we talk about keys, when we talk about things like that, we're leveraging this kind of theory. But this kind of theory, while it seems really basic, and I'm probably giving everybody here a real refresher course on it, is something that we can take in some directions that we probably didn't really expect. Now, the second thing that we have to understand is this concept of derived data. Now, Postgres is really, really good with derived data, right? We can take one piece of information, one fact, and we can derive another fact from it using a function of various kinds, right? You know, a good example would be, you know, you're using PostGIS, you have a multi-polygon, you want to find its area. For a given multi-polygon, you're going to always have the same area, right? Assuming that we're talking about like the same SSRID, or SRID, and so forth, right? So we put that in, we get a single value out. That's also a function in this case, okay? What's not a function? Random, of course, right? Random doesn't take anything out and in, and it gives you arbitrary stuff out. We call it a function, right? And this is why I'm being careful with my definitions. But mathematically, it's not a function. Programming-wise, it's a function. So again, you know, if we have an uppercase string, a lowercase string is a function of that. And you know, we can extend that idea in many, many different ways. Now, the key thing here is this concept of referential transparency, and it's what relates to what we call in Postgres an immutable function. Now, a function is referentially transparent in computing terms if it's a mathematical function. Namely, if you can take the output and you can substitute it for the program call, okay? So, like I've just said, you can look at functions both as input and output related or as unique correspondence related, right? And referential transparency means those are equivalent. The other thing that is required for a function to be referentially transparent is not only that it has unique input to output transparency, but also that it doesn't do anything else, right? So if you write data, that's a side effect, and the function's no longer referentially transparent because if you substitute the output for the function call, you don't get that data written. If you're logging, you know, and you need to see those logs don't get written, right? So those aren't referentially transparent, and we need to understand that mathematically they aren't functions. Or if we just want to call them that, they're not referentially transparent. In Postgres terms, we would not mark them as immutable, right? So now I want to take just a moment and talk a little bit about how Btrees work. I don't know how many people here are comfortable with understanding Btrees as a data structure rather than just an index type. So a few of you. A Btree is basically, as we see here, basically you start with a node and then you have slots and pointers to other nodes, right? And so in an ordered index approach, this gives you sort of an arbitrary n factor for you know, extending your search. So you scan each node linearly, but that's usually really fast. And then your links to the other nodes are going to be a little more expensive, but you know, but then basically each of those can be the root of its own Btree. So we need to be able to think about that when we start looking at what Postgres can actually use an index for, right? So Postgres also has some really advanced indexing capabilities, and in many cases, many other databases don't even have these capabilities, right? Or they may have some of them, but not all of them, and things like that. The first one, which is going to play a really big role in my first example, is expressional or functional indexes. How many people here have used expression-based or functional indexes? Just a few of you. And these are actually really powerful, and if you don't know that they're what you can do with them, they may not seem as important, but they can actually solve a lot of problems for you. The second are partial indexes. How many people here have used partial indexes? Even fewer. Partial indexes allow us to index only a set of rows, a subset of the table. So we don't actually have to index the whole table. We can just index part of it. Index-only scans. We can actually build our indexes around being able to do index-only scans. In certain cases, that can be a real performance win. That'll be my second case study here. My third case study will be partial indexes. And you know, as I mentioned before, there are many, many more index structures besides Btree. GIN indexes are amazing. You can do some interesting things with them. Gist indexes, quite interesting. Then you have RUM. You have a lot of sort of external index types that have been built by other people over the years. So these are the advanced topics that we're going to talk about here. In this particular talk, we're going to talk about functional indexes, partial indexes, and index-only scans. So we're going to go on to our first use case here. Case was, I was working on a very large database. I think at the time it was around the 10 terabyte range. And in that database, basically that database was a giant life sciences research assistance database, right? So the idea was you get genomes that are, you know, processed. You're trying to find proteins. Those proteins are then looked at for what other proteins they resemble, so we can infer what they do, all the rest of this. And all that information is getting stored in all these different tables. The biggest one is called documents. Documents has some various metadata fields. It has like a document type and some other things. Then it has a document field, which is text. The document field stores some sort of scientific, structured, machine-readable text. Now, I said some sort because not all records store the same type, okay? Some are EMBL format that describe genes that are found. Some are some other format that describe protein structures. Some describe like the chemical properties of different parts of a protein sequence. But the one that's really important for this are the ones that describe patents, okay? Somebody from product comes along and says, for this particular page, we need to look at the 5 most recent patents on a given protein sequence, because if we want to spend time researching this and developing this protein, we want to know whether there's any possible patent conflict. Easy enough. Only 10% of these rows are patents, maybe less, and where's the patent date stored? It's in that text field. So what's the first thing that somebody tries to do? Oh, wait, this is a nice web application. We have all this logic in the middleware. It's in Perl. We can just extract this information and display it in the front end. Problem is, you just pull 5 patents, try to pull those into the front end. You're not necessarily getting the 5 most recent, right? So that doesn't work. You can't grab your data set and order it in the front end. That usually doesn't work. We also decided that we didn't really want to reprocess the whole table if we could avoid it. So, and we don't want to add a new field for something that is only affecting a small number of records. Yeah, I know that you have the null mask things. It's not going to add that much storage to the table, but that table's already 6 terabytes, and you know, if you're trying to add all this information for everything else, you're going to have various different kinds of problems. So, what did we do? Wrote a function and an index. Now, the nice thing about PL Perl is it's trusted, and it's really good at extracting a little bit of information from a text field. For any of your procedural languages for this, it's the ideal language for this particular application. I know Perl's relatively out of favor these days, but Postgres doesn't really have an alternative that has these particular capabilities. Then we index the output of the function, and we integrate that into the front end. Now, one of the really interesting things is because of the way Btrees work, we can actually use them for 2 things. First, we can use them to locate records matching certain values or a certain range of values, but we can also use them for searching for a certain number of ordered values, right? And so if we have this index in, now suddenly Postgres can do all of the ordering and stuff for us very cheaply and very easily. And so here's a simple example. I didn't add the fact that I believe we actually made this a partial index also. And I didn't include the Perl source code because escaping in LaTeX is difficult and it wouldn't fit very easily onto the same slide. But basically, we start with a function that takes in the document type. Now, the document type is the table name, right? Because in Postgres, your table is also a type. You can then pass it in, you can pass in a whole row to a function as a single argument. And that makes deriving data based on a particular row really easy, and it gives you some other really nice syntax things that we could use to, say, integrate this into the ORM. We just have to say, oh, there's this column you didn't know about called patent date. And because of the fact that you can actually write this then as document.patentDate in the column list, the ORM can just use it as if it were a column. It won't work in all cases, but in most cases it will. Then basically it checks to see if the document type is patent D, and if it is, then we look at the document text field, and we extract the patent date out, and we return it as a date. Relatively easy, and we can note that it is immutable. I don't think I noted that on the slide, but we have to state that it's immutable. And once we state that it's immutable, Postgres knows that we believe that this function is referentially transparent, that it's a true function, right? Then we create the index, and yeah, I did note that it's a partial index. You'll note the syntax here is a little bit funny. In this particular case, you can't do document.patentDate because the parser won't evaluate that as an expression in those cases. So you have to use the functional notation there, and then basically this goes through and it preprocesses everything, but it does so without adding a new field, and that's kind of important sometimes when you're dealing with these very, very large systems. Downsides to this approach, and then I'm going to take some questions on the first one. This requires some integration with the ORM layer. If you're using an ORM, that may pose a problem for you. It may not. Fortunately, as I say, Postgres has this notation where if you're passing in a row to a function, you can then say, the name of that row dot the function name, and that'll work just as is. But you can only have one argument, and it has to be the whole row. And then the second issue is that if you modify the function, it invalidates the index. You have to re-index at that point. Obviously, that's important for Postgres to do that, because if you didn't, then you might look up a value that's no longer valid for that function call. So there are some problems with that, and that leads to some caveats, and then people have to be careful. Common thread you'll see here is this issue of added complexity with many of these tools. So this is the first of the case studies. I'd love to hear questions about that before I move on. Any questions? You? No, okay, another question? I don't see any questions. All right. Then I will move on. Same project. I'm going to get into just a piece of the database schema in a second. But somebody decides, basically somebody from product comes over and they basically say, hey, look, we have a new business need. When we're doing development on a new protein, we want to restrict who can look at it, okay? And we don't just want to restrict access to proteins, we also want to restrict access to genomes. So if somebody's doing research on, I don't know, like the CVent metagenomes or something, nobody can look at any of the proteins that we've identified from that sample. Okay? This was on Postgres 9.4, I think. So we didn't have row-level security. As you'll see, it wouldn't have really made a big difference. The big issue here is they wanted to write this data only to the protein and the genome because they were afraid that if you have multiple copies of this information that it may get out of date, and then people may see things they're not able to, they don't have access to, or things might be hidden when they're not supposed to be hidden. So it's really important to have this work right and all the time, and so basically the decision was made, this can only be written authoritatively in authoritative places. The problem is, the data, the pieces then get written to the tables on the ends there, and if you want to look at some table in the middle, you have to check both ends. So now you're implementing row-level security across joining 5 tables. Anybody want to guess how well this performed when they put this in place? Not very well, as I'm sure you can imagine. Remember, this database at this point is probably 10 terabytes, maybe approaching 12. So the fundamental question is, how fast can you get it? Can you get it fast enough that the researchers will be okay working with the system? Doesn't have to return queries in milliseconds, but can we at least try to get it to return queries in seconds and not, say, minutes? Different options, we could accept this poor performance, and in the short term, that's what everybody decided to do. We could replicate data to all tables. We were told to don't do that because of these problems I mentioned before. So, hold on, I'm just gonna grab a little bit of water. So, how did we solve this? We decided to see what we could do to optimize the disk I/O. Now, one thing that's kind of nice about this is that while we had all the write-ahead log sitting on spinning Rust, the actual data was sitting on SSDs, right? So random access is relatively fast. Still not quite as fast as sequential access, but it's still pretty good. And so indexes, in addition to dramatically reducing the amount of I/O, also dramatically reduce the sort of the complexity of the sort of I/O costs that we were looking at. Because typically you'd have to go down the foreign key index, then go to the heap, and maybe there may be multiple dead rows. You'd have to basically do all of that within the heap. And that was a big part of the performance problem. So we decided to try to do this with index-only scans. Now, the idea of the index-only scan is to make traversing this join tree as cheap as possible. So the idea is that for anything where we don't actually have to look up anything on the heap, let's just index the values that we need to transit the join so that we can make that process as quick and efficient as possible. Now, there are a couple immediate problems with this approach. The obvious one is now you're tied to a join order. And if you want to support both join orders, both join directions, now you need duplicate indexes, and that's going to add performance problems when it comes to writes, right? So what we did was we identified the join directions that were most likely, and basically, in most cases, you start with the foreign key and you're going to move over towards the primary key. But in a few cases, it might be cheaper to go the other way. So what we were able to do is to basically create multi-column indexes where you start with the foreign key and then go to the primary key. And as long as vacuum is reasonably keeping up, you most of the time don't actually have to hit the heap. And because your primary key is always a single value, it's going to be a functional, it's always a function of your foreign key. By the time you've hit that foreign key, you already know the primary key, right? You don't actually have any more disk I/O that has to happen to make that additional lookup than you would just from transiting the foreign key index alone. So that actually sped things up to the point where it was slower than before, but it was actually quite tolerable. Now, downsides to this approach, it really constrains the join orders that the planner can do, because suddenly one join direction is a lot cheaper than another join direction. And so if you're trying to troubleshoot or think about why are we getting join performance issues, suddenly you have these extra constraints that you've imposed on the system. And those constraints are going to give you some difficulties if you're not already aware that this is going to happen from the design phase. You can, as I said, try to support both join orders, but if you have a lot of writes, and this database in some cases had a lot of writes, you're going to end up making each of those writes a lot more expensive, because now multiple indexes have to be updated. So, any questions about this scenario? No? Okay. This is moving a little bit faster than I had planned, so hopefully we'll have some questions near the end. Now, the final scenario I have has to do with partial indexes. Now, this was another place I worked, place where I have given a lot. I should just turn off Telegram, but I will. But this place that I worked, basically we had a large distributed database environment. We had more data than I think I've ever managed to put on Postgres. Our log environment was 10 petabytes when I left, but this particular piece, we had around 2 petabytes of data distributed around, I want to say 100 servers or so. Now, the problem is, basically, this data is coming in, it's hitting these point of entry servers, right? It then gets processed on the point of entry servers, and from these point of entry servers, it then incrementally updates another set of servers, right? So these point of entry servers log everything. They basically handle all the incoming events. It was an ad tech database. And then little pieces of this go out and get updated somewhere else, right? You get incremental updates on these other systems. Now, you have 10, 20 terabytes of data per point of entry system. Those get compressed down with only, I think, about 1 year or so of retention. And that data then goes to this warehouse system that stores data for all time. I think going back at least to 2012, I think at that point. So I would say at the point where I was seeing this for the first time, it was already 5 or 6 years of data. And basically, you still have some initial, basically you have these incremental updates, right? Those are then, of course, both are distributed platforms. So the question is, how do we do these incremental updates in a way in which we can still capture data if we need to change it from months ago without having massive indexes that are literally reducing the amount of data that we can store and retain on these point of entry servers. Now, the amount of data that we're actually have to index is very small. We're talking about maybe a few 100,000 rows out of millions and millions and millions and millions, possibly billions on these servers. So definitely don't want to index all the data. That will lead to terabytes of data waste. So we have a trigger, updates a field called materialized. We have a partial index where materialized is true. And basically every time vacuum runs, it's going to effectively prune that index down so we can then keep it small. Downsides of this approach. You need to understand that there's an index there that's only there for that materialized piece, right? You can't expect similar queries that aren't hitting where materialize is true to perform nearly as well because they can't use that index. Otherwise, it worked pretty well. I mean, of the three, this is the one that added the least complexity. So are there any questions about this, this piece before maybe I go on to conclusions and general questions? All right. So for the conclusions, the first thing I'd say is that these advanced index functions are actually really, really, really useful. They allow you to sometimes do things that would be much, much more complicated if you tried to do them by actually adding a value and indexing it or indexing the whole thing or things like that. The big problem is that if you think, okay, well, we have an index and that index hits a column and things like this, that's a real simple mental model to keep in your mind. Once you start adding expression-based indexes, functional indexes, partial indexes, now suddenly you have to think a little bit more clearly about exactly what's indexed, you know, what happens if I redefine this function? Is it going to give us some performance problems for you know, the application? And that's a very real concern in many cases. So this adds complexity, and that complexity can bite you if you're not aware of it. So this comes back to, I think, a really important piece of advice that I was given by my college calculus professor when he said, in mathematics, power tools are considered inelegant when hand tools will suffice. In other words, these are all power tools. They're great when you need them, but in the event where you are sitting up and you're not sure you need them, maybe try a simpler approach first. So when I say these are crazy things, they are crazy powerful things, but they can also be insane things. I'd like to make some particular thanks, particularly Novozymes. It should be AS, not AB. They're in Denmark, not in Sweden. I need to change that. They were the life sciences example, and I learned a whole lot about big Postgres databases there. And then Adjust GmbH was the partial index example. I also want to thank Timescale. They send me here, pay my way, all that sort of thing. And one of the reasons why they're really interested in that is because a lot of people do things like time series data, and they'll store it in JSON formats. And once you start doing that, expressional indexes and functional indexes are actually really important. So that's the thank you to them, and also noting of the relevance. I'd like to open this up to general questions.
Yes, hi. My name is Catherine. Closely. Okay. Hi, my name is Catherine. Thank you for your talk. In our previous talk, a speaker has mentioned some bad, quote unquote, use cases for indexes, and one of them were for rare use cases. And I was wondering if your first case study was a rare use case, and I was wondering how you went about choosing indexes as the solution.
So thinking about the rarity of a case is important in this. As I say, you make the difference between a power tool and a hand tool, right? So I think it's definitely, well, I mean, okay. Let me preface my answer to that by just mentioning sort of when we talk about the 3 V's of big data, we're typically talking about volume, velocity, and variety. And where the functional index and functional and partial index combination becomes really, really helpful is where you have a large variety of data, right? In this particular case, we had this big table, and it had a text field, and that text field could have a bunch of different formats in it. So that's a good example of a relatively high variety data set. Like compared to what I would say is sort of standard, sort of the standard Postgres use cases where people are using Postgres as a purely relational database, that would be a relatively rare setup. But once you start dealing with the semi-structured and high variety data, then it's suddenly a lot more common. So I would say, yeah, it's a relatively rare use case. But it's also a use case where that happens a little more often than you'd think.
Thank you.
There's one over there.
Another questions?
Okay. Yes, there's one over there.
This is 2 questions. So can you say something about where and how you ran this, on what kind of hardware and how was it configured? And then in getting such an engagement, if that's the way it worked, I mean, obviously you're very Postgres expert, but was there any consideration of using either the large cloud tables, Bigtable or Redshift or something like that?
Okay, great questions. I'll start with the the hardware question. The life sciences database was running on a large Dell server with 3 terabytes of RAM, and I think it had 24 physical cores, 48 virtual. Everything there was run on premise largely because it was a very high throughput workload. When I left that project, there were 1,000 cores devoted solely to scientific processing of inbound genetic information. So that more or less ruled out cost-wise putting everything on the cloud. Now, on the third one, basically each of the point of entry databases, I think, was a Dell. Yeah, it was another large Dell server. I'm trying to remember the specs. I think R240 or something. I'm not 100% sure on that. They had 380 gigabytes of RAM, and we didn't put that on the cloud because basically with the amount of data that we had and the number of servers that we had, the business would simply never have been profitable. So like, when you're spending 20,000 euros a month on hosting, and that's all bare metal, and you have to figure if you were putting that on the cloud, you'd probably spend 5 times that. So those were the considerations there. Thanks. Any other questions?
Thank you.
Thanks.
So thanks again, Chris. So in 20 minutes, we have Postgres Ask Me Anything session. And we have Bruce Momjian, the Postgres person in here. Is if you don't, I mean, you have to meet Bruce if you are dealing with Postgres. He's one of the very few people who actually created Postgres. So here we go. So in 20 minutes, see you soon. Thank you.